All right, so we've extracted, we've either downloaded our data and we've processed it. So this is part 3 of a tutorial on how to model and map sea level flood risk with sea level rise. So in this section, what we're going to do is we're going to look at how we begin to identify areas that are prone to flooding under the different scenarios. So I said earlier that one of the things that we need to take account of is the fact that one, the DEM is dealing with meters as a measurement, both horizontally but also vertically in terms of the height of the land. So if you're measuring the height of the water relative to the land, you've got to be using the same units. And then secondly is the issue of how do we take into account the different the datum that's being used. So the height of the land that's being displayed in the DEM is using a particular model or a benchmark from which to measure height. So let's revisiting what we'd done previously when we were calculating flood currents. We used these heights for minor, moderate, major floods, and so that 12.5, 14, and 15 foot refers to the height of the water. And if you recall from when we look at the National Weather Service site, that height is relative to mean lower low water, MLLW. Which is one way of measuring height of water, so basically the really low tide line. But there's other ways of doing that. And so as it turns out, we saw in the properties, the raster that we downloaded, the DEM, they don't use MLW, they use NAVD88, North American Vertical Datum 1988. So what does that mean? Well, if we go back to the assignment, we were looking at coastal flood. One of the links that was in there took you to a web page that shows datums for, if I can get there. Hold on, let's turn that off. Okay, sorry, I'm having trouble getting it. There we go. One of the websites takes you here to illustrate the point. So, as I said, the Weather Service uses mean lower low water, which on this illustration is depicted by this value down here, MLW0. So that's the starting point. And we know that the height of the water varies across the day because of the tides. But there's other ways of deciding where to start measuring from. So obviously, one other one that's common is mean sea level (MSL). You could certainly measure from there, being aware that the difference. The NAVD88, which is listed here, is shown on there, and it says 5.51. And what that means is that that datum point to measure from is 5.5 feet above mean lower low water. So it's a higher starting point in terms of measuring height. It's kind of close to mean sea level, it's just slightly above it. So in essence, what it means then is that the elevations of the land that are shown in that DEM are all measured relative to that point, NAVD88. So they're starting at a higher point. So that means then that when we measure the height of the water, we're kind of ignoring the stuff that's the stuff that's below that. So in order to harmonize our flood heights, we have to turn them into the same datum first, and then after we do that, then we've got to convert them into meters. So how do we do that? Well, if we go back to our modeling here, right? One thing that we could do is we could say, well, okay, let's see what that looks like. If we took the minor flood height, for example, right? So right now, the water has to rise 12.5 feet above mean lower low water to cause a minor flood. But if we're starting from NAVD88, that datum, we're kind of starting at a higher point, so the water doesn't rise as high. And so we could say, okay, let's take that water height and just subtract that difference. 5.51 is what it was. Okay, so now if we do that, what we see is that relative to that vertical datum NAVD88, the water needs to rise just almost 7 feet in order to hit that minor flood height, right? So that's what it means. So that will put it, that adjusts it for take into account the different datum, right? So we could do that for all 3 flood heights, and we can see their adjusted heights relative to that new datum. But the second part of that thing is that in addition, we know we're going to need to work in meters. So we're going to have to adjust these from feet into meters. And so that's pretty easily done. So look, if you Google that, the conversion is pretty simple. It's basically take whatever feet and multiply it by 0.3048. So I'm going to alter this equation slightly and say, okay, let's take that, subtract that height to make it the same datum, and then multiply by 0.3048. There we go. Okay, so then now we have a water height that's in meters and relative to the North American vertical datum, right? So I'll copy that over to the other three. All right, so now now a minor flood means that the water has to rise a little over 2 meters relative to the North American vertical datum, right? So that's two conversions there. Now, that tells us today, right? So today, a minor flood, the water has to rise by that much. This will allow us to do the modeling on the map. But what about the future scenarios? So this is where it gets a little different, or not different, but we're just going to take it a slightly different tack. So previously, in order to kind of account for the changing likelihood of floods, we subtracted the sea level rise projection from our heights, right? In order to basically show how much easier it is to get to the height. But what we're going to do in the mapping is we're going to map out the reach of these floods. We're going to keep essentially their probabilities steady, so that we're going to assume that minor, moderate, and major floods in the future have the same probability of happening. It's just that they reach further inland because the water's higher. That's basically the approach that we're taking. So what that means then is that what I want to do is I want to be able to model the higher water height with sea level rise. So in essence, what this means very simply is I want to take these water heights that we've got going on right here, and I'm just going to add that height, 1.2 feet, to it. But again, this is 1.2 feet, right? So that has to be turned back into meters. So what we have to do then in that case is we need to convert that to meters and then add it to our original water heights. So in this case, what that looks like is I take this value right here and I'm going to multiply it times the conversion factor, 0.3048. So that turns it into meters, right? And then I take that value and I add it to this height over here. So what that means then is I'm taking the water height in meters, sea level rise in meters, and adding it to the height of the minor flood level, or vice versa. So I see that under that scenario, the new minor flood water height in the future is 2.5 meters, right? So that's what I'm doing right there. So in order to carry that forward, I'm going to be wanting to hold that this part of the equation steady. So I'm going to put that in dollar signs to hold that steady. And then in addition, I want to hold so that's the only change right there, right? So when I bring this across, it's going to add the water height to the relative. So I see that for the major example, it's adding that extra little height of sea level rise to the major flood as well. So I want to repeat that for the others. But keep in mind that for each of these water heights, right, so sea level rise is always relative to that original height. So you want to make sure that you're always referring back to that. So again, we're taking the sea level rise amount, converting it into meters first, and then adding it to the original water height over here, right? And then this part where we have the sea level rise, that one always stays steady. So we hold that steady with the dollar signs, right? So then we have the new minor water height under that. That's the 2050 scenario. And then we have one more over here with the 2070 scenario. Again, we're taking our value here, converting it to meters, and then adding it to the water height over here originally. And got to keep this part steady. So I want to hold, there we go. Great. Okay, and then we can copy that this way. And I'll just double click on it just to make sure it's calling to the right cells. Yeah, so it's basically adding this sea level rise amount converted in meters, adding it to the original water height for a flood of that height of that stage. Okay, so now what we have here is the new values of the water height that constitutes that level of flooding under the different scenarios. The situation today, 2030, 2050, and 2070. So what I'm asking you to do is to do all 4 scenarios. So you'll have 4 maps, basically, showing what it looks like and illustrating what that risk looks like. But to show you how to do it, I'm going to pick one of them and do that one, and then and then you can just replicate that for the other 3. So we're going to focus on 2050. So we're going to look at this middle scenario. So I'm going to essentially map out what areas would flood under a minor flood with that water height, and the moderate and a major, and then we'll label the map so that it's clear what it is that we're looking at.